understands what it is. All right, everybody getting this? All right. And that's the entire algorithm. Any questions? We go until just before 4, so we have 20 minutes or so. Everybody good? Yeah? Uh-huh. No.
How am I going to know
What the loop invariant is?
0, 0, or 1?
All right, so in 3101, if you're with me, you will do weeks of loop invariants. Right? In this course, I'm going to give you the precondition, I'm going to give you the postcondition, I'm going to give you the loop invariant, I'm going to give you the Java code. Right? You need to, how deeply do you have to understand them? What I tell them in 3101 is the loop invariant might be really confusing. Why? Because we have a confusing algorithm. It's not clear where we are in the middle of the algorithm. So don't try to understand it. Just try to maintain it, right? But here, we're doing really simple problems. If you can't understand the loop invariant, then you should. Right? It's going to be a simple loop invariant, right? So you're going to say, yeah, that's a reasonable loop invariant. That's reasonable code for maintaining the loop invariant. And then you're going to give me metacode to do it. And is it going to be this long? You know it's not going to be this long because you don't have enough time. Right? Does that make sense? I think it's fair. Right? All right, so let's do another example. All right? Now, the problem is we have two integers. Now we're going to multiply arbitrary integers. Remember we said you can't do arbitrary integers in one time step. So it's going to take more than one time step, right? Oh, and are we multiplying and we're adding? We're probably going to add because adding's easier. Two integers representing strings, output is their sum, all right? Multiplying is harder. We want a linear time algorithm, right? We're going to add them. All right, so here, what's our algorithm? Is you sum the first characters, you write the low order digit, you remember the high order digit, right? Then you shift over. You read the next digit, you add it to the carry, you write the low order digit, you remember the high order digit, and you move over, right? Everybody got adding? That's what we're going to do, right? What's the algorithm, right? Don't worry about the whole computation. Worry about the loop invariant, right? Loop invariant. So, loop invariant. Loop invariant. Oh, what do we got here? What's our loop invariant going to be? Is that the lowest I minus 1 digits of x have been read, right? The lowest I minus 1 digits of the sum have been produced. And what do we have in our blackboard? The carry, right? All we know is the carry. Everybody good? So, how are we going to maintain this loop invariant? Now, have I told you the entire loop invariant? No, I said it's been read, and I said it's been written, but we need a data structure. We have to figure out where we're going to put all this stuff. All right? All right, so here's some Java code, right? We're going to have a variable called carry that remembers the carry. Initially, our carry is 0. I told you the loop invariant, right? When we exit when we're at the end of the input, in which case we have to write the final carry, right? If we haven't inputted, then we're going to have local variables, right? And these local variables are things that we're going to remember temporarily, but we don't have to remember in the loop invariant. Right? When we're at the loop invariant, we're only going to remember the carry. But temporarily, we're going to remember these other variables. And then somehow we have to read the next characters. Right? We have to read the next x, the next y. I don't know where they are. We have to figure out where they are. We've got to find them. We've got to read them. right? And then what do? We take our value of the carry and we add it to these characters. And that gets, this is now a 2-digit number, right? If this was 9 plus 9 plus 1, then that adds up to 19, right? So the carry becomes the 10, becomes a 1, and we write the 9, right? Does that make sense? And then we deallocate this memory, and we're back up, and we just know the carry, right? Everybody getting this algorithm? Right? Everybody good? So now let's write let's write Turing code for it, right? Now I still haven't said where the numbers are located, so we have to think about that, right? We have to think, how is our X and Y encoded, right? They're long strings, so are they encoded like this, or are they encoded like this? Do we have 2 tapes maybe? 2 tapes would be great. 3 tapes would be even better, right? How are we going to do it? How do we represent the output? Where do we put the output? Right? These are all questions that we have to ask, right? What is our tape alphabet? Well, let's have our alphabets be 0 through 9 maybe, so we're reading characters, right? All right. Right? So our characters could be 0, 9, right? Binary would be a little too hard, right? Then you would also have to be translating, right? Unless we're adding in base 2, we could be adding base 2, in which case it could be binary, right? All right, so how are we going to do all of this? So let's just sort of be a little vague. Let's say somewhere on the tape will be the input. Somewhere in the tape will be the X, and somewhere in the tape will be Y, right? And somewhere on the tape will be the output, right? That's our precondition and our postcondition, right? And then what's our loop invariant going to be, right? Right? We need a loop invariant. So the loop invariant can do what we did before. We establish the loop invariant, right? We write the carry on the board. Right? Everybody, that's all we have to do to establish the loop invariant. And then how do we proceed? Right? How do we maintain the loop invariant? We have to say what the loop invariant is. Well, somehow, right? Somehow you have to remember what we've done before. So maybe we blank them out, right? Or maybe here's another trick that I like. Suppose you want to keep it, but you also want to blank it out. One thing is to have a bigger tape alphabet, so you write on top of a 7, you write a 7 prime. Right? You have an extra character. Right? No, here's what our characters are. We're going to have the character 7, and we're going to have another character, which is this. Right? So you can write that on top of the 7. So anyway, somehow we keep track of, like we did last thing, we keep track of where we are. And so what do? Well, we have to read in that 7, right? Now, we can't, how much of X can we read in? We only can remember 1 character of X, right? So we read 1 character of X into our states, right? So now, Pooh Bear is remembering this 1 value, right? And then what do? Right? How many have we read? We read 1 value. Oh, there we said. We remembered which one we read. Right? Then we move. Somehow we know how to move to the next guy. Maybe those other guys have been blanked out. Right? Somehow we move to the 6th. And we remember the 6. Right? And then somehow we do the math. And we can do all the math in our heads. Right? The table lookup. And then we have to move to the output, and we write the number. Right? Does that make sense? And then we need to reestablish the loop invariant, so we go back somewhere to the input. Right? And we repeat that. Right? Everybody got that? And we could formalize that into state transitions, and we won't. Right? Everybody kind of get that that's kind of a thing that we can do. Everybody good? Right? We maintain the loop invariant and we're good to go. Right? The bulk of, right? What's the work here? The work is moving the head. Right? In fact, what is the running time of this algorithm? It's going to be n squared. Why? It's because I have to add n digits. Right? And each time I add a digit, I have to walk around all of the digits. It's going to take me time n to walk around, right? To go past the x, go past the y, find my place in the z. That takes me time n. But I have to do it for every character, right? So that's n squared. And people are getting restless. Are we running out of time? We have 4 minutes. Excellent. Right? All right, so let's talk about multi-tape Turing machines. All right? So we said a Turing machine only has one tape, but we can have multiple tapes. Right? You can have as many tapes as you want. In fact, you could have a grid. Right? You can have any sort of design different machines. So in this kind of machine, we're going to have a separate head for every tape. All right? Because each tape can be in a separate head. And so what do we know? Now we have to design the delta function. Right? So the delta function knows, right, the Pooh Bear knows what state it is in, knows what character is under each head, and based on that, decides the new head, new state, decides what character should write under each head, and whether each head should move. Right? So here's our delta function. Says if I'm in this state, and head 1 is reading C1, head 2 is reading C2, right? Then I go into this state. I write this character under the first head, and I move this head this direction. Right? Does that make sense? All right. I think I have 1 minute left. What can we do it, right? So here's an example, right? Here, I'm in some state. I'm reading an L, I'm reading an E, I'm reading a 5, right? What do I do next? I go in this state. I write a Z on top of the L and a 7 on top of the E, right? Here, that becomes a Z, and that gets moved. That becomes a 7, and that gets moved the other direction. That becomes a T, and that head stays in the same spot. Right? Does that make sense? So, I got 2 more minutes. Don't move. 2 more minutes. We can finish adding. All right? So now suppose I have 3 tapes. Right? And I can have on the first tape the X, and the second tape the Y, and the third tape the Z. Right? So now life becomes easier. Right? How many lines of code do you think we're going to need now? How many states, total states, do you think we're going to need? 2. All right? Would you believe 2? Good. So here's the code, right? So here's our loop invariant, right? We've read, loop invariant says the head is showing us the next character to read, and the first 2 characters have been done already, and they've been written, right? Yeah, they've been added and written. And what am I remembering? The carry. And I'm in line 1. I'm in line 1, and I'm remembering the carry. So what do I do? Right? Right? All I'm remembering is the carry. Right? So, what's our transition function? It says, if I'm in state, line 0, carry 1, then what do I do? And I'm reading a 3 and a 1 and a blank, right? Then what do I do? Right? Right? You say, what do? I write the 1 and the 3 and the 1 there because I don't want to bother with them. and then I 3 plus 1 is 4 plus the carry is 5. I write a 5 there, right? What do I do with my heads? I move them all, right? What state am I in? I'm still in line 0. I'm done. I can go back. My loop invariants are done. I'm in line 0, and I'm just remembering what the carry is. And this time the carry is 0, right? There, an entire program with 2 states. Good? Now, I will see you guys at the test. No. Let me turn this off. Don't save that. This